So my name is Nikolay. I'm a developer technology engineer at NVIDIA. This is my, I think, third presentation here. So I've been here already twice, presented twice over the past couple of years. Today we're going to talk about GPU architecture, some programming model features. We only have 1 hour, so it's going to be very quick. But at the very end, we also have we will have a hands-on with some more kind of, you get some experience programming GPUs as well in the evening. So how GPU acceleration works in general, you have your application code and you have CPU processors, you have GPU processors in your system. You probably want to utilize both. Often it doesn't make sense to port everything to the GPU or leave everything running on the CPU. And because GPUs are really, you can use them as accelerators, it makes sense to profile your code, see what is your where is the most compute intensive part, where is your bottleneck, and try to move this part to the GPU, right? Because you don't want to move, let's say, reading from file or processing some stuff that is CPUs are good at. And maybe there are some parts of the code that are sequential, and it also doesn't make sense to move to the GPU in that case. So the main idea is you take your application, you find your parts where you can parallelize, and then you move them to the GPU, and then you leave the rest code on the CPU. And this way you can get the best performance because you can utilize both processors. Now, obviously, today's systems, they're very complex, right? You have CPUs, multiple sockets maybe. You have also multiple GPUs on your system, and each GPU has its own memory. Then there is system memory, and GPUs can now also access system memory directly. So it's all very complicated to program, but I'm going to go into details like what tools are available and what options you have to program these systems. But the thing to remember here is that each GPU has its own memory, which is very fast. So if we dive into the GPU architecture, so these blocks, so we have multiple GPUs. Each GPU has its own memory, which is at the bottom, DRAM. Then it has its own L2 cache that is shared between multiple streaming multiprocessors, which we call SAMs here. And from one architecture to another, there could be different number of SAMs, but the general trend is it's increasing. So on Kepler, it was like 15 SAMs, and then it was on Maxwell 24, and then it goes up. So you have a lot of these streaming multiprocessors that are connected to a shared L2, and then to DRAM, and then they can also access system memory or other GPUs memory through PCI Express or NVLINK. Now, if we go deeper into architecture, so we have DRAM cache, DRAM, L2 cache, and SM. So I'm going to go over some SM architectures that we had before, starting from Kepler, which is still available and still being used quite often. For example, Oak Ridge Titan supercomputer still has it. So in Kepler SM, what we have is, and as I mentioned, there are 15 SMs per, for example, Tesla K40. And then each SM has some set of functional units that can do operations like FMAs and some other like integer operations and loading, storing, and other stuff. And so these functional units, they're connected to a register file, and then going kind of far from the functional units, we have also L1 cache, shared memory, texture cache, and constant cache. And so this is on Kepler SM. And the numbers are here. So each SM has effectively, so we call them cores, like CUDA cores. And we have 192, 32 single precision floating point cores, and 64 double precision floating point cores. What it means, cores, is that each SM can effectively do 64 floating point instructions, 64 FMAs per clock, essentially. And so if you multiply this by clock and the number of SMs, you effectively get your teraflops for the GPU. And so GPUs can do more single precision ops than double precision ops, for example. And I'm not showing here integer ops and other operations, more complex, but they're also there, but they have lower throughput in general. Now, register file is 256 per SM and shared memory, and we'll go into a bit more details like what that actually means, but the thing to remember here is that it's a limited resource, right? So you have limited amount of shared memory, you have limited amount of register file. Shared memory is more like explicit cache on GPUs, so you can put something in there, reuse it as you like it, and then put something from shared memory back, write it to global memory, for example. But there is also L2 cache, L1 cache as well. So they're sitting together, and you can switch. On Kepler, you could switch between 16 kilobyte L1 cache and 48 kilobyte shared memory, or vice versa. And now texture cache is similar to L1 cache, but it has some additional features. Texture memory is a special memory that you can do some filtering on in hardware on GPUs. You can also do some out-of-bounds checking automatically, and so you can save some instructions on like computing out-of-bounds and some things there. But the general principle is the same, and there is also constant cache. So constant memory is a memory that you typically write from the CPU once, and then you access it on the GPU, never change it on the GPU, and it's a small chunk, but it has its own separate cache, and so it's cached there, so it's very fast access to it. Okay, so Kepler was introduced in 2014. Now, the next architecture was Maxwell. I'm skipping that, so I'm just going to go over Pascal, which is the one we announced, I think, last year. So Maxwell didn't have any good double precision compute. So Pascal is very similar to Maxwell, but it has more balanced double precision, single precision. So if you compare on Pascal, we actually have 64 cores, FP32 cores, and then 32 FP64 cores. So the throughput of double precision ops is just half of the single precision floating point ops. Register file is the same as on Kepler per SM, and then shared memory is also kind of in the same ballpark, slightly more. But you can notice at the bottom here, so we actually have like almost 4 times more SMs on a single GPU versus Kepler. So on Kepler it was 15 SMs. On Pascal it's 56 SMs. And another thing changed if you compare to the previous slide. So if you look at the SEM picture, so we unified our caches. So now we don't have a texture and a one cache. So now they're all unified into a single cache we call unified cache, but it's also just a texture cache. And shared memory is still there, but you can no longer switch between different amounts of shared memory and cache, so they're completely separate. And there's still constant cache. Now the latest architecture that we just announced, at GDC this year in May, it has slightly more changes to the SAM. So for example, now we don't have this unified cache, but now we're back to L2-1 cache and shared memory. And we also completely got rid of texture cache, so now everything goes through essentially a L1 cache. So that's, and it's a more, it's a better one cache. So for more details, you can look up some. We have a white paper on Volta, but it provides better performance in general on applications. Another thing changed is, so number of FP32 cores and 64 is the same, 64 and 32. So throughput is similar per SM, but again, we have 80 SMs versus 56 on Pascal, so it's increasing number of SMs. Register file is the same. So big changes, we have now also tensor cores, which can do some interesting things here. So it's essentially each tensor core can do matrix multiplication. It's very special, so both matrices are 4x4, and they have to be in FP16 precision. The multiply is FP16, but then the sum, when you sum up all the columns and rows, you get 32-bit precision. So effectively, each tensor core can do 64 FMA with mixed precision FMAs. And it's very powerful for deep learning, but why am I telling you this? Because maybe you can find use for some of your applications as well, for HPC applications. And here's just kind of summary of all the things. So if we look at, we know how many SAMs we have, we know what's the clock, what's number of cores we have, so we can actually compute flops for all these different architectures. So starting from Kepler, Pascal, and Volta. So you can see the trend, it's increasing. Pascal is twice as fast as K40, and then Volta is, I think, 50% in general better. But then the tensor core performance is obviously it's just beyond 100 teraflops because of these special cores. Now, this is mixed precision, of course. So this is not like FP32 or FP16. It's kind of mixed, multiply 16 and then sum in 32-bit. Now, memory-wise, just to give you some idea, each GPU has, so these days, mostly 16 gigabytes in Tesla cards, and Kepler K40 had 12 gigabytes. And bandwidth is also increasing in general. So from Kepler to Pascal, it was a big jump. Then from Pascal to Volta, the peak bandwidth did not increase significantly, but the achieved bandwidth is actually much better. So the utilization of the bandwidth on Volta is, I think, beyond 90%, while on Kepler it's mostly on Kepler, and Pascal it's mostly around 80% is the maximum you can achieve of the peak. For instructions, so these numbers you can pretty much achieve again on gems or matrix multiplies. You can get, I think, beyond 5 teraflops, double precision on Pascal, for example, so 90-95% for gems. It's very easy to achieve. Okay. So now I'm going to go over some best practices for GPUs. So what kind of things you should look for, when you're developing a new application or porting an existing application or developing a new application for GPUs. So first of all, GPUs and CPUs, they're designed differently. So CPUs, they're designed to minimize latency because they have branch prediction, they have caches, large caches. So each thread can do complete its work pretty fast. Now GPUs, they are designed not to be not to be fast per thread, but to hide this latency. So when a thread needs to load something, some memory, or it needs to do some expensive operation, we can switch between threads very quickly and not see any significant penalty from that. So CPUs are designed to minimize latency, and GPUs are designed to actually hide this latency. And in fact, if you look at the clocks for the GPUs, they are usually lower than the clocks for the CPU, for example. And we also, on the GPU, we don't switch between individual threads. We switch between group of threads we call warps. Each warp is 32 threads. And on this picture, if you look, so for example, on the CPU, we have a thread, and it needs to do some processing, and then it waits for the data to load, and then it does some other processing, and the data is usually in cache, so it goes pretty fast. Now, but it's sequential. And then on the GPU, we have these warps that are 32 threads, and each warp, to load up all this data, it takes quite some time. So what we do is we then switch to, let's say, from warp 1 to warp 2. Then the warp 2 does some processing, and then switch to warp 3, and then the warp 4. By the time the warp 4 arrives, then we can switch back to warp 1 and continue with that. So the context switch is pretty much for free on the GPU, and we achieve good efficiency by hiding these latencies. This is the very fundamental idea behind how GPUs can achieve good performance. Another idea is, of course, to be able to hide this latency, you need to have a lot of threads to switch, a lot of warps to switch between, from one to another. And because of that, if you look at your problem and develop, some program that is that doesn't have a lot of parallelism in there, you probably won't get a good performance for a GPU. So you need to expose a lot of parallelism, run a lot of threads if possible. So this is a very simple example. You can, parallelize by rows, or maybe you can parallelize, each element, each thread processes its own element, and then you get more threads significantly. So in general, fine-grained parallelism is good for GPUs, and then coarse-grained parallelism is bad for GPUs, but it's usually good for CPUs. Now, when you so the first thing to look when you have a lot of threads, you probably find you develop an algorithm that is parallelizable, and the next thing you should think about is how can I distribute the data or distribute computations between all my GPUs and all my CPUs in the system. And it's very important because if you think about it, all these bandwidths that I showed, like 700 gigabytes per second for Pascal, and then CPUs can have like up to 100, I think, or maybe more gigabytes per second. So the weakest link is going to be between CPU and GPU, or between GPUs. It could get better. So for PCI Express, it's something like 12 gigabytes one direction. But then for NVLINK, it could be 20 gigabytes per link in one direction. But nevertheless, it's still order of magnitude lower than your GPU bandwidth to its own memory, or CPU bandwidth to its own memory. And so first thing to think about is how you can parallelize application, and then make sure the data stays, kind of trying to minimize the transfers between different GPUs or between CPUs and GPUs. Because that's probably going to be your main bottleneck. Like if you just have a reduction kernel written in CUDA on the GPU, and then you have your data sitting in the CPU memory originally, right? It doesn't make sense to actually run this kernel at all, because you're going to be all your time will be spent in moving this data from the CPU to the GPU, and then even though the kernel will run super fast, you will still be bottlenecked by this interconnect bandwidth. So it's probably better off just running it on a CPU, unless you have some additional stuff to do with this data, and then maybe you can amortize this cost of data movement. And another thing, so we try to minimize data movements between devices. GPUs are really good. You can also do compute and communications in parallel. So what we could do is we could copy the data, maybe divide it in chunks, and copy the data in chunks, and then start processing of some of these chunks before we copy the whole thing over. And that's a very common pattern in many GPU applications. So when you have, let's say, an application that needs to do some compute on the whole domain, like a 3D grid or something, and then you do some communications with your neighbors, what you can do instead, and then you have a dependency, right? So you need to process this whole domain, and you need to do the communication part. Maybe what you could do is, in some cases, you can start processing your boundaries only, and then you can run the communication part while you're doing the compute on your interior, for example. And so in that case, you can overlap some of the things and maybe even hide the communication part, right? So you can potentially hide your expensive, PCI Express transfers or NVLink transfers and get better performance. All right, so kind of moving closer to SM, right? So we can minimize data transfers on a level, a system level between CPUs and GPUs, or between GPUs. But then also, often it makes sense to try and see if you can use all of these resources that are available on the SM, the ones that I talked about: shared memory, registers, constant memory, all these things. And there are many different ways you can use them. So for shared memory, you have to explicitly use it. You have to explicitly allocate some shared memory and then put some things in there. Registers, you can control that, how many registers your kernel is using. But the thing here is that by using all these resources and maybe even trying to block for L2 cache, you can actually reduce the traffic to DRAM, because obviously bandwidth to L2 cache and bandwidth to shared memory is significantly better, and to registers even more, than bandwidth to your global memory. So if possible, try to, instead of loading all your data from DRAM all the time, maybe you can try to put it in shared memory and then reuse from there. It's going to be much faster. Or maybe you can reuse some of the data in registers. Instead of loading it up, you can just load and register and then reuse it on the next iteration. Of course, when you try to use all these resources, at some point you're going to hit this problem that it's a limited amount of shared memory that you have. It's a limited amount of registers that you have. You can't put your whole problem in your shared memory, for example. And this is where the trade-off comes. Am I going to run more threads per SM maybe and use fewer resources, or do I want to use more resources per thread but then use fewer threads? And this is where occupancy comes into play. So occupancy is essentially a metric of how many blocks or how many warps we are running on SM versus the maximum amount of blocks it can run. So occupancy of 100% means you're running all the blocks you can, so like 32 blocks on Pascal, for example, and you're running all the threads, so like 2,000 threads per SM. And then if you, let's say your thread starts to use more shared memory, then your occupancy can go down. And eventually you have this trade-off, well, if I'm going to use a lot of resources on the SM, then I'm not going to run a lot of threads and might be inefficient. And there are ways to check it, the occupancy, and we have good profiler tools. I don't have it in my slides, but we'll have actually a couple of slides on profiler. But there are ways to check your occupancy and try to play with it, how many registers you want to use. Maybe you want to increase that or reduce that and see how it works. And then often, when you increase your occupancy, it doesn't really mean that you're going to get good performance, because at some point, kind of adding more threads doesn't really, hide more latency. You still have this latency to hide, so it doesn't really improve your overall performance. I have a good slide to show that. So if we just create a very simple copy kernel, right? So copying from one location to another. Just one thread loads one element and writes to another array. That's it. Very simple. Let's look at the bandwidth that we can achieve for this, for different GPU architectures. So have dotted lines. This is for Kepler, so at the bottom. And then solid lines there for Pascal P100. And then different colors mean different types of data that we load. For example, we can load float or float2, so more data, or float4 even. And on the horizontal axis, we have occupancy. So it goes from like 1/8 to 1 essentially. And then on the, so the values are actually achieved bandwidth that you can get. So if you remember, I showed for Pascal, the peak bandwidth was 732 gigabytes per second. The achieved one, you can see it's roughly 550 gigabytes per second, around that. And then what you can see, the trend is, and then for Kepler, it's 288, and then the achieved is like 250, I think, around that. So the trend here is that if you have low occupancy, maybe just do some other things. So in our case, we just artificially limit our occupancy. But then maybe you have some shared memory you're using or lots of registers. In that case, your application becomes latency bound because you're not be able to hide these latencies because you don't have enough threads to switch between, right? The thing I mentioned in the beginning where you need warps and be able to switch between them to hide latency. So if you don't have all these warps, then you cannot hide latency, and that's why you become latency bound. And it's clearly shown here. So you can see that the bandwidth that we can achieve even with this simple copy kernel is significantly lower than the peak bandwidth when your occupancy is low. Now, another thing, so if you increase your occupancy, general trend is that your performance goes up, right? But at some point, it doesn't really change. So for example, with this, if you load float4, then even like 25% occupancy is good enough. So if you increase that, you don't see any difference here. However, when you see differences, if you just pick one particular occupancy factor, let's say 50%, then switching between loading a single 32-bit floating point or loading float 2, for example, it's clearly better when you load more data per thread. So that's another point. So sometimes when you're increasing your occupancy, you might not see better performance, but you can get better performance when you do more work per thread or load more data per thread. And OK. But then another thing, how can you know? So this is a very common example. How should you structure your data access to be more efficient from the GPU, right? Because it could be completely scattered, and it could be just accessing some some local chunk of memory. And GPUs, they have caches, and it works very similar as on the CPU. But the big difference here is that we look at the accesses per warp, right? So we don't look at this individual thread accesses. We look at the whole warp, 32 threads. And if this whole warp accesses one cache line, then we're going to move this cache line. If this whole warp accesses completely scattered locations, then we're going to move all these locations, and it's going to be very costly. So the actual cache line is 128 bytes, but the transaction size for latest GPUs is 32 bytes. So whenever you access scattered access, you're actually going to be moving 32 bytes per thread. So in this case, for example, if all threads access completely scattered locations, we have 32 transactions of 32 bytes. Versus in the best case scenario, it's just one cache line or 4 transactions of 32 bytes. And the difference is like 8 times essentially. However, in the second case, we're also effectively allocating 32 cache lines of 128 bytes. And this also limits our effective cache size. You can actually do some experiments and see that for yourself. But the main idea is that you want to have your threads in a warp accessing some consequent memory region, so to be able to reduce this memory traffic, that is coming. And not only you need to make sure your warps are kind of converged, trying to access have some data locality. They also need to be, in general, following the same execution path as well. So on the GPUs, when we hit a condition branch, for example, and if your threads in your warp need to follow different branches, then what's going to happen is that first, the first part of your warp will execute this branch, the first path, and then all threads will be basically, the rest of the threads will be idle, and then the second part of the warp will execute the rest of it, and then the first part will be idle. So all these branches are serialized essentially. The way it worked on Pascal was that actually, if you have multiple statements in your branch, then all of them will be executed first by the first half of the warp, and then the second, all the branches in the second part will be executed. On Volta, we could actually switch between branches because threads have their own program counters. But the idea is still the same. You still have this divergence, and still threads are idling, so it's not good for performance. And there is no issue when when you have some branch divergence between warps. So for example, if this condition was not based on thread index, but based on warp index, then this would be fine, because we can switch between warps easily, what I already mentioned. But if you have some branches within your warps, then this is usually bad for performance. And maybe in some cases, it's possible to restructure your program to avoid these branches. Then one of the last things I want to mention regarding performance and good practices, best practices for GPUs. And this is what I already mentioned. When we load, it makes sense to do more work per thread in terms of loading more data, or even doing more operations per thread. And I mean independent operations. So this is a very simple example. we have a loop where we just sum up all the things together and compute logarithm. And if you just execute it like that, essentially we'll have to load the data from memory, compute logarithm, then add it up, load another one, and there's dependency on all of these instructions. So they have to be executed one by one. If we change our code and in this case, for example, on the right side, we maintain 2 registers and compute odd and even indices kind of in parallel, right? So independent of each other. What's going to happen is that GPU will be able to run these different instructions and issue them in parallel. And this might improve performance because you no longer have, you don't need to wait for your, let's say you issue a load to your B0, but then you don't need to wait for this to come up to issue a load to B1. So you can issue multiple loads independently and you can hide latencies better. So usually doing more work per thread helps a lot, and there are many ways you can achieve that, right? So you can load more data per thread by, as I showed before, using float or float 2, float 4, or you can do some loop unrolling and do some more independent instructions per thread and increase your LP essentially. So it helps with performance a lot. Okay, so just very briefly about different ways you can program GPUs. So we covered some of the architecture details and how you structure your algorithm to make use of GPUs and improve performance. Now, what are all the tools available to actually use GPUs? And we have 3 big blocks: libraries, compiler directives, and programming languages. Libraries are really good when the problem you're trying to solve, maybe already solved by someone else. For example, you have DGEM or matrix multiplication. You don't need to write it yourself. Just use, we have CUBLAS, and there are other third-party libraries available as well. So you can just use these libraries. So it doesn't make sense to start from scratch unless you're trying to learn how GPUs are operating and trying to create a nice parallel optimized implementation just for kind of studying the GPUs and trying some stuff with optimizations. If you just need to use, then it makes sense to use libraries. And we have libraries for all the different things. So I mentioned CUBLAS, there is CUFFT, there are sparse libraries, and there are solver libraries like MGX, where you can do multigrid, algebraic multigrid. There are deep learning libraries like CUDA. There are random numbers, Thrust. So Thrust is very interesting, is because you can. So it's more like a STL library for GPUs. So there, if you need to do, let's say, you have 2 arrays, and then you need to add them up, or do some transformations with them, or do something with it, like reduction or scan. Thrust is good for that. And there is also a similar library called CUB, which is more, so it's only for GPUs. Thrust can actually run, it has execution policies for CPU and for GPUs. So you can run the same program on CPU and GPU. CUB is GPU only, but it lets you use all these primitives like block scans and others, reduction scans and others, inside your kernel. So if you need to do a scan in your, let's say, CUDA block or something, then you can do that on the SM with CUB. But these are kind of nice libraries to know, and I very often use either Thrust or CUB in my day-to-day job optimizing applications. Okay, so these are about libraries. We have many more. It's just like a short list. Directives, we're going to have a hands-on on that in the evening, because it's probably the easiest way to get into GPU programming. With directives, you don't even need to handle your data movements, although you can. And I'm going to go into more details later on in the evening. But the main idea is you have your loop or multiple loops, and you just add some pragma ACC. It could be a data movement, or it could be kernels that will create some kernels around it. And you can specify some additional options for your loop, like how many threads you want to create and things like that. So it's very simple. And you can run the same program on the CPU or on the GPU, so it's portable, which is good. I'm pretty sure there is a target. So there is a target for CPU, GPU. I think there is one for Xeon Phi, either in development or already available. So it's very portable across all these. And for ARM, I think also either in development or available. But of course, libraries, for example, they're super optimized, right? So with using cuBLAS, you can get 95% of your gem, peak performance of the GPU. When you do these things, this is portable, but it probably won't be super optimized. You can probably write the CUDA kernel that is going to be better or faster. Sometimes, not often. Like if you have a very simple copy kernel, then you can just instrument it with pragma ACC. It's probably going to be the best one you can get, even if you write it in CUDA or use libraries, for example. But there are some cases where writing a custom kernel can be more performant, because here you don't have a lot of options. Like you put some hints for the compiler. Please create a kernel for me, and it tries to figure out all the things on his own. And when you write your own kernel, you know what you're doing. You can use shared memory. You can put things in different order and do all this crazy stuff. But this is good for kind of getting started with the GPU and getting a feel of how a GPU performs. And at the same time, you can get all the data movements and stuff. So it's very nice. So CUDA, this is how CUDA looks like. So on the left side, there's CPU. On the right side, there's CUDA C code for the GPU. So main difference, so we're just running Saxp example here, very simple. So in CUDA, you need to write your own kernels, as I mentioned, and you annotate them with the global, which means, and you need to compile it using a special NVIDIA compiler in VCC. And it will generate CPU code, host code, and GPU code as well. And CPU code will be running this kernel on the GPU. And this is essentially the kernel. So you can look at it, and it's very simple. It's very similar to the CPU code. The main difference is that because we're running this in parallel about multiple threads, we need to compute for each thread its own index. And this is I, essentially. You compute your own index. You check if you're not out of bounds, and then you just compute the same instructions that you have here on the left side. Then this is the kernel. And then to launch this kernel, you need to specify how many blocks I'm running, how many blocks, how many threads per block I have. I'm not going to go into details what is a block or what is a grid because we don't have time. But effectively, it's a way to structure your threads into some hierarchy so that you can have blocks offloaded to different SAMs. So we have this hierarchy of SAMs. You have 80 SAMs, and then on a single GPU, how do you distribute work to all these SAMs, right? And this is a way to provide that. So you can specify, okay, I want to run, let's say, 256 threads per block, and then I'm going to run 4,000 blocks. And then each block will be dynamically distributed to different SAMs. This way, we can balance things over very efficiently. And also, if you run this program on another GPU that has, let's say, 10 SMs, then it's still going to work because we're going to distribute it to all these 10 SMs instead of 80 SMs. So this is the way to kind of structure the thread hierarchy and make it portable between GPU architectures. Another nice thing is Lambda. And I want to mention it because Lambda in C++11. We started support this with recent CUDA versions, but it makes things even easier when you write your CUDA kernels. So you don't actually need to write a CUDA kernel in that case. You can just use Lambda function here with the device Lambda function. Same code, and then for each, this is coming from Trust as well. So effectively, we're running GPU code in this case, but we don't need to write a separate kernel for the GPU code, which can make all your CPUs very easy to browse. You just replace your for with this for each, and then you get your GPU kernel. And you can even think about maybe having an if-def, and then you have, let's say, 4 each or 4, depending on your CPU or GPU, and then you can have your portable code with CUDA, essentially. So it's a very powerful feature, very recently added, but it's a way to write things in CUDA without writing kernel separately. All right, and then the last part is going to be about memory management. Because it's a very important thing in GPUs, as I mentioned, being able to control where data moves. And here I'm going to talk just about the memory movements from system memory to GPU memory. But I'm not going to talk about how to load things up in cache, and this is all we covered a little bit in the beginning, how you can coalesce memory and things like that. We're going to talk about how you have a lot of your data structures in the CPU memory, how can you move this to the GPU memory, right, when you want to use it on the GPU. So there is a way to move data manually if you want to. And to do that, so we have some, let's say, CPU code on the left side. We allocate some memory, do some stuff with it, free. So on the GPU, what we could do to access this memory, we could allocate some memory on the GPU. We could copy it over. So we can allocate on the GPU. We could, we update something on the CPU. Let's say function 2 we want to move to the GPU, right? So we have the same code path as here, but then we decided, okay, function 2 is very expensive. We want to move it to GPU. So what we do in that case? So we allocate some data chunk on the GPU with CUDA malloc, special call, CUDA API call. Then we copy this from, after we complete the CPU1 function, we can copy data from the CPU to the GPU explicitly using CUDA memcopy. Then we execute GPU function. Then we copy data back. And then we proceed with the function 3, right? So this is how the code would look like. And the only missing piece here is we need to write this GPU kernel, right? But then memory-wise, this is going to look like this. So you're going to have allocation, memory copy, and then freeing. 2014, we introduced unified memory, which is a way to simplify all these things and provide more natural way to program GPUs. So with unified memory, what you could do is you can actually use the same pointer as on the CPU. Now, this actually won't work today, but it's right now you have to use special allocator. So malloc is not going to work, but you have to use a special CUDA malloc managed allocator. But in future, very soon, it's going to be enabled in Linux. And so you will be able to use just malloc, just regular malloc. So you still do the same thing as on the left side to CPU function 1, but then you don't need to allocate some data pointer, some data on the GPU and copy it over, copy it back. You can just access it directly. So what is going to happen is that the data will be migrated back and forth automatically, and you don't have to worry about this. So it really simplifies your programming, and especially when you're just starting out and maybe porting some parts of your code to the GPU, you probably want to write your CUDA kernels, but you maybe want to avoid the hassle of moving the data structures to the GPU. And if you're reusing this data, so for example, if your data fits in GPU memory and then you're running your kernel over and over, then the overhead from the initial migration could be amortized easily in this case. Another example why it could be useful. So again, so let's say we have not just, like this case is very simple. You have like linear data and then you just copy it over. What if you have some linked list of some data, like a double pointer essentially, right, with some additional data? It's very common. Maybe you have more layers on top of that, some hierarchy. So to do that with explicit memory management, you need to do this deep copy, right? So allocate for all these pointers, then copy the inner pointers, then copy the outer pointers, and then run the function. It's very easy to mess this up, and you can easily get like all sorts of errors and issues, and you're going to debug this and then spend a lot of time on this. With unified memory, you don't need to do that at all. Like you can just reuse malloc. Well, in this case, as I said, like right now we have to use CUDA malloc managed, the special allocator, but it's going to work just like that. And I'm going to go a little bit over details how unified memory works, because it's kind of magic, but there is some logic behind it. So just so you know, because it's important to understand how it works to make sure you're not losing any performance and you make sure what's happening. So we have 2 processors. It could be CPU, GPU, it could be 2 GPUs. They have their own memories. And generally, they have their own page tables as well. And so you have some pages that maybe there is a page allocated in memory A, and then there is a page in memory B. And the virtual addressing is the same, right? So you kind of have the same address points to page 1, and then page 2, page 3. So if, for example, processor A accesses page 1, then it's its own local memory, so that's very easy. So you just access it directly. But then maybe processor B tries to access page 3 that is not even allocated. Let's say it just writes to it. What's going to happen is there's going to be a page fault triggered, and the page will be populated in the memory, in the processor B's memory, page 3. And maybe the next thing, processor A tries to access some pages that are not local, not resident in memory A. And then, again, it's going to trigger page faults. And then pages will be migrated, either over PCI Express or NVLink between these processors. And then, again, processor A just accesses it locally. So this is how it works in general. So, and when you access something, it's not in local memory, it's going to be page fault, and the page will be migrated. What it enables also is that if your memory is full, you can oversubscribe it, so you can access something that is not in your, like some page that is well beyond your physical memory capacity. You have all your pages allocated. In that case, the driver will figure out which page to evict. It will evict the page to the processor B, and then migrate page back to the processor A. And so you effectively get an oversubscription on the GPU. So you can use as much system memory as you have, and the memory will be migrated kind of in chunks and pages to the GPU. There is also a way to use atomics. So for example, if 2 processors want to do some operations on the same page, some interconnects, like PCI Express, for example, we have to use exclusive access. So effectively what's going to happen is that the processor B will do some local access to this page, and processor A will trigger a page fault, and then the page will be migrated, and then there will be local access to. Due to this unified memory, how it works, and on-demand migration, we kind of automatically get this atomic access because of the separate page tables and exclusive access. Sometimes when you have, for example, NVLink, the remote access, so it provides a remote access and native atomics, so you don't have to migrate page and page fault on it to do atomics. So this, for example, works on DGX1 system where you have 8 GPUs, they're connected with NVLink together, so they don't have to migrate pages to do atomics between them. All right, I'm going to go briefly over some details how you can use unified memory. As I mentioned, first thing like the easiest way to opt into unified memory is to use CUDA malloc managed. So just for, instead of all your malloc, just use CUDA malloc managed. You can still use this memory on the CPU, but you can also use now this memory on the GPU. Now, there is a way to use it in Fortran as well, and OpenACC. And in future, there will be a way to just use malloc with Linux, but there's some work going on for the patches, HMM patches. Very briefly for the profiler, because now if you imagine you have this automatic memory movement between GPU and CPU or between GPUs, you want to know what's happening. Maybe the data is moved that you don't want it to be moved. So there are ways to control that, but there are also ways to check what's going on. The profiler, this is how our visual profiler looks like. So you can see all the memory movements, the brown lines. You can see addresses. You can see explicit migrations and implicit migrations as well. You can see all the kernels. So we could probably have a separate session on profiler, just that. But there are many ways you can play with it. You can filter it. Maybe I want to look at particular array and where it moves to, between GPUs. So you can see, filter out the edges and maybe just the read faults on it, for example. And then you can also correlate with the source code. So if you see a migration that is maybe suspicious, you can click on it and you can see where in the code the allocation that corresponds to it. And as I said, there are hints that can be used to control some of these things. For example, you have your data allocated with CUDA Malloc managed. You can access it directly on the GPU. Then the page will be migrated, right? As I said, kind of on demand. But this will, involve a page fault, which is expensive. And if you know that you're going to access data on the GPU, you can still use unified memory, but maybe you can optimize with CUDA mem prefetch async. So this is a prefetch. It's more like a CUDA mem copy instruction. It's more like explicit moving the data. But instead of, in CUDA mem copy, you copy the data. Here, you just move the data, so it will remove all the mappings from the CPU as well. It's a way to optimize your application sometimes. So maybe you can start with on-demand migration and just avoid all the explicit calls to memory movements. But then later on, you can switch. If you figure out, OK, I'm actually losing a lot on these page faults, and then maybe you can switch to CUDA mem prefetch async to optimize that. I'm going to show some numbers on that as well. And then the advice is, the CUDA mem advice is a way to set, I want this memory to be preferred location. For example, you can set preferred location, CPU, GPU, or different GPUs. You can set, I want this memory to be directly accessed, to be able to directly access this memory from this certain processor. Or maybe I want, the last one is read-only. So maybe I know that the data is going to be only read from, and so the driver can do some data duplication instead of moving data. Just a brief look at the performance. So I mentioned you could access data on demand, or you can prefetch it, or you can mem copy it, right? So, or you can just do CUDA mem copy. And so there are all these lines here. So the blue line is mem copy. The brown line is prefetch, so CUDA mem prefetch async. And then the green lines are just direct access, so on-demand access through unified memory. This is the buffer size on the horizontal axis, and these are gigabytes per second for PCI Express 3. So like 12 is effectively the best you can get. And you can see that prefetch and CUDA mem copy, so this is from CPU to GPU and from GPU to CPU. And there are two lines for green. I explain what it's that. So the solid line, so there's just different ways you can access data from the GPU. So solid line is just access one thread, accesses one element. And then the dotted line is we have one warp accessing a 64K page. So effectively, one thread is accessing a lot of elements. And performance is different. So first thing, prefetch and mem copy have similar performance. That's good to know. So you don't have to use the old way of doing CUDA mem copy. You can use all the benefits from unified memory, having a single pointer, and then doing prefetch if you want to. Then you can get pretty much the same performance as mem copy, maybe slightly lower. And then for on-demand migration, it usually depends on your access pattern. So if you have, and for example, a question why the streaming pattern is lower than the one where we have warp per page is because of the page faults and the way we process them. Because in this case, you have each thread will generate, or essentially multiple page faults, or maybe each warp will actually generate multiple page faults. And then we'll have to sort them, remove duplicates, and process something. Well, in this case, we actually have just one page fault per warp. And so it's much more efficient in that case. But the bottom line, it will probably depend on your access pattern. So you will not get the same bandwidth. Even if your size is large and you access data one by one, you can get different performance with on-demand migration. OK. And the same thing for CPU. If you use single thread or multiple threads, you can see different performance for on-demand migration. So here, the dotted line represents the multiple threads accessing the data from the CPU, and it's much faster than just single thread accessing the data. And here are just the plots for NVLINK, just to compare. You can look up the slides, but the trend is the same. All right, so I'm just going to summarize because I'm just running out of time. As I said, for unified memory, it makes sense to use it when you're just starting out and maybe you have your old big code that you have a lot of data structures and you might want to use unified memory just to focus on kernels and for a little while forget about your data movements. And then you can get back to it and then insert prefetches where necessary and get all the same performance you would get with CUDA mem copy. But it helps a lot with portability as well. And you can get some nice features like oversubscription, as I mentioned, automatically. So if you run out of memory, you don't need to worry about it. OK, so yeah, that's kind of the summary of the unified memory. And then for additional resources on the GPU, here's the list. I would definitely recommend to look up CUDA programming guide. This is the main resource for any like GPU-related or CUDA-related, all the information there essentially. And then the on-demand GDC, there is a lot of recordings over the past like 7 years or 8 years of GDC on all different domains, all different applications. So it's a really nice source for information when you're looking for a particular problem. Has anybody done this problem before? What they did with GPUs? And so you can actually like just type your CFD or maybe a particular algorithm, and then you probably will find a few of the presentations already available at GDC. Block, parallel for all block is very nice resource as well because we engineers post usually there all the nice CUDA tricks and how you can use this and that and all these features, some new features. So it's very, it's always get updated so you can get the latest information about some of these things. All right, and the self-paced labs is something we'll cover in the evening. All right, that's it. Thank you. Questions? Okay, 2. Yeah.
When you talk about Lambda,
yep.
Do you pay any penalty by using Lambda, or?
No, there is no penalty. So it's the same kernel will be like generated a kernel, then called from the host. So I don't think there's going to be any penalty at all. It's just convenient.
What's the difference between managed memory and mapped memory?
Between managed memory and what? Mapped memory? Yeah, so the mapped memory, sometimes like we call it zero copy. So it's the memory that is pinned, for example, in the CPU memory. So it's pinned to the CPU memory, but you can directly access it from the GPU memory. The main difference is with managed memory, your data can migrate to the GPU. With pinned memory or zero copy memory, the data stays in the CPU. And so if you're going to reuse it, then you're going to lose. You're going to always pay this cost of interconnect between CPU and GPU. So, and there is way, it's actually kind of overlapping these terms because with managed memory, you can actually pin it as well, so that you can use the advice hints that I mentioned, set preferred location, and you can set it to the CPU, and then effectively it becomes a mapped memory from that perspective, because now it's pinned in the CPU memory, and then it's not going to be migrated because the driver will resist all the migrations because of the advice that you set.